How can we theoretically extend the lifespan of the sun? What would be the best way to change the orbit of the Earth? And would we ever dive into Uranus? And in Q&A Plus, would Planet 9 even be categorized as a planet if it's ever found? All this and more in this question show. It's time for the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops into your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. RobH. Is it true that we don't know the distance of Polaris from Earth? And if so, what does this mean for our use of Cepheid variables? Does it cast doubt on the use of standard candles? We know the distance to Polaris. It is 446.5 light years plus or minus 1 light year. So the uncertainty to that measurement is about 1.1 light years. So it could be a little bit closer or a little bit farther, but it's pretty close. And Polaris is just one Cepheid variable that astronomers measure. They are aware of thousands and thousands of them. And originally, the distances to the Cepheid variables were measured very roughly and very carefully using the astrometry method. So you measure the angle in the sky to Polaris or any other Cepheid variable or any star, really, when the Earth is on one side of the sun, and then you wait 6 months for the Earth to be on the other side of the sun, and then you measure its angle in the sky again, and then you're watching to see how the star moves against the background of all of the other stars. And so over the course of the year, you're going to see the star kind of bounce back and forth. And the example that I always use, right, is hold your thumb out at arm's length and then just open up one eye, close the other eye, back and forth, and you'll see your thumb jump back and forth in your field of view. And so that's what the astrometry method does. The parallax method is that you're able to measure the distance to the star because it creates a triangle. And you're able to measure that using trigonometry. And the parallax method kind of has its limits. We can only measure out a few thousand light years away. It depends on the brightness of the star. Dimmer stars, it's not so easy. Very, very bright stars, you can measure them farther out. And so astronomers had measured the distance to a bunch of these Cepheid variable stars. And then they were able to track the pulsation of those variable stars, use that to calculate the intrinsic brightness, use that to realize that you're really just, when you're watching the pulsations of these stars, you're able to know how bright they are. And then you just measure how bright you see it. And that allows you to calculate how bright it is. And that allows you to tell how far away it is. And that's the method that they use to calculate the distance ladder. And because it is the first rung on the distance ladder, it is the most important rung. And so astronomers put a lot of emphasis into measuring checking and double checking and remeasuring and making sure that their measurements to the Cepheid variables are still correct. And so every few years, we'll see a new science paper where, some astronomer has gone and redone the calculations and confirmed that they are, yes, indeed, still correct. And of course, we got the Gaia mission, which came up from the European Space Agency a few years ago, which was like the most comprehensive measurement of astrometry, the parallax method, for like 1 billion plus stars in the Milky Way. And so we've learned a tremendous amount about the structure of the Milky Way, the distance to stars, the movements of stars, thanks to the Gaia mission, which is doing this astrometry parallax method at a vast scale. So we know the distance to Polaris, we know the distance to thousands of other Cepheid variables. We check them, double check them, and use that as that first rung on the distance ladder to measure the distance to other things in the universe. Dad a Monk. Could we ever reach a point technologically where we could add fuel to the sun to prevent it from expanding into a red giant and extend the habitability of Earth? The problem with adding fuel to the sun is that we would actually make it live for a shorter period of time. The more massive a star is, the shorter its lifetime is. And so you want to do the opposite. You want to extract material away from the sun. You want to take away its mass. And then that will sort of counterintuitively, right? It will make it last longer. Like if we had the kind of technology to actually refuel the sun what we would probably want to do is turn the sun into 13 stars. So we would use a technique called stellar lifting. So we would draw material off of the sun. You could use powerful magnetic fields, or maybe you could spin up the sun and you could extract material off of it. And then you would collect it over into a smaller star. And you just keep doing that until you had 13 red dwarf stars. And maybe you put them in some kind of orbit where they're all orbiting one another. And now each one of those is going to live for 10 trillion years. And that's better. Like, that really gives you some time to hang out. So no. Now, the other thing is, if we had a way to mix up the interior of the star. So the problem with the sun is that it's got the center, the core, which is where the fusion is happening. And then outside of that, the temperature and the pressure isn't high enough. So fusion can't happen, but also you don't get convection. So you have this whole big region called the radiative zone. And it is this firewall to the convective zone, which is the outer part of the sun, where you have these sort of blobs of material that rise and fall inside the sun, carrying the heat out and releasing them to space. And when you look at the surface of the sun and you see these granules on the surface of the sun, these are the tops of these columns of bubbling material that are coming up from the radiative zone all the way to the surface. And it's mixing, but it can't reach the core because of the radiative zone. While with a red dwarf star, they are fully convective. So the whole star is bubbling and convecting, and it's using up all of its fuel, while the sun is only going to use up the fuel in its core, and then it's going to die. And that's only about like a third of its size. So there's tons more fuel that the sun could use. So if you want to save the sun, you just want to bring a big spoon, and occasionally you want to just mix it. Mix up the sun. You can get fresh material into the core. It can continue fusing, and then you can extend the life of the sun. But the best way to do it is to tear it up, 13 pieces, 13 stars, 10 trillion years. It's time to shout out our new patrons at the $5 level and above: Ralph Martinson, Matt Denning, Stephen, Ronald, Tim Paget, Scott Martin, Charlie Jacob, Mark Briscoe, John Kitchen, and Jan Rodricks. Join our community at patreon.com/universe today. Me is the explosion of satellite mega-constellations and space debris making near-Earth orbit dangerously unsustainable? Not yet, but it is not moving in the right direction. So space is really big, and so there is a lot of room for a lot of stuff. But over time, the more material that you have in orbit, the more that stuff is going to collide with each other, and you're going to get that debris colliding with other debris, and eventually you're just going to get more and more debris that's in the region. For the place where the satellite mega-constellations are going, it's not as big of a risk as you might think, and that is because they don't last very long. So there are, and I forget the numbers, now it's hundreds, maybe even thousands of Starlink satellites are deorbiting every year because they are, they've run out of propellant, and they're re-entering the Earth's atmosphere, and they're burning up. And so even if there was debris, it would clean up in a very short period of time. Like within about 5 to 10 years, any satellites that are in that area get cleaned up. And so if the satellite mega constellation stopped launching and nobody was able to continue to boost up their satellites, within about 10 years, that area would be clear of satellites. There would be no satellites anymore. And so if we get to this place where people are like, oh no, we've got too many satellites, then people stop launching them for a while, a bunch re-enter the Earth's atmosphere, the area starts to clear up, and then you've got room to launch satellites again. It's the higher altitudes where it's a bigger problem. So, say below 500 kilometers altitude, like where the International Space Station flies, that region cleans itself up within a very short period of time. Once you get up to 800 kilometers, which is being considered for some satellite mega constellations. So OneWeb flies at that higher altitude. Those will last a couple of decades. And then once you get above 1,000 kilometers, now you're looking at, a century. Once you get above 1,200, 1,300, then you're looking at multiple centuries. And if you get higher than that, then things are going to practically last forever. And so the bigger risk is not where the satellite mega constellations are going, the biggest risk is the higher altitudes, because they just don't get cleaned up. But at the same time, those regions are bigger, and so there's more space for it. And so I think people are really worried that we're going to fall into this Kessler syndrome, where one day we're going to wake up and too many satellites have crashed into each other, and now there's just this metal shell around the Earth that you just can't launch anything new. And it's not going to feel like that. It's that right now, satellites have to make several course corrections every year. That, someone is tracking all of the pieces of space debris, all of the satellites that are orbiting around the Earth right now, and all of the satellite companies are watching the trajectories of everything else that's out there. And if something looks like it's going to be uncomfortably close within the next day or so, they'll fire the propulsion on their satellite and they'll shift its orbit so that it misses, so it gives you more room, more space. And that uses up the propellant on the spacecraft. And so the more stuff that's up there, the more of these random possible interactions that are going to be happening, the more you burn through your propellant, and the more quickly you're out of propellant, and then your satellite will be sucked back down into the Earth's atmosphere. And the right solution is for the world to come together and to agree on where we put satellites. That, if we're going to have satellites, they're going to be observing this part of the Earth, they go in this direction, they move at this speed, at this height, and then we go this way for another one. The way that we have flight paths, or the way that we have directions that cargo ships travel in the ocean, that, instead of it just being a free-for-all with cargo ships crashing into each other, think about highways, right? Like, instead of people just like go ahead, just use the highway however you want, right? No, you stay on one side of the highway, and that minimizes the chance there being a collision. And so we need to move to this future where the satellite operators are held to very specific orbits. And that will mean that we can then put a lot of satellites and not worry about them crashing into each other. But we want to be really cautious about anybody using those higher orbits, because that's where they don't go away. They stick around for a very long time. Dillon Callihan, how close will other star systems get to ours? They can get relatively close. Within every million years or so, a star system probably comes within, say, a quarter of a light year. So there's the next one is like 1.3 million years, Gliese 7 something, I forget the exact number. So it's another star system that's going to come within about 0.25 light years of the sun. So this happens, when you think about, if that happens every million years, imagine how close they've come in the billions and billions of years that the sun has been around. And yet, none have come so close that they've significantly disrupted the orbits of the planets. Like, you'd have to get much, much closer to actually start to disrupt things. So they can get close. And this is sort of like been thought of as a really cool idea for how you might be able to jump from star system to star system. So instead of creating interstellar spacecraft that will take you 10,000 years to go to another star system, wait until a star is getting very, very close, and then you just hop over. AllanWorks, is there any possible way to scientifically move a planet? Yeah, theoretically, you can use an asteroid. So when an asteroid flies close to the Earth, we get a little bit of a tug of its gravity, and that slightly changes the orbit of the Earth. And so if you wanted to move the Earth, and sort of the classic example of this is if, the sun is heating up, it's giving off more and more illumination every year. It's going to be heating up planet Earth. In about 1 billion years, it's going to boil the oceans on the planet. So you want to be able to move the Earth outward a little bit every year to match the energy output of the sun. And so if you bring one asteroid relatively close to the Earth every, it's like 10,000 years or so, then you can slowly move the Earth's orbit out at a rate that matches the increasing illumination from the sun. So you do it with asteroids. Stratton Henson, how do we know for sure that space rocks can't collide at such speed that one shatters and bounces backwards as if they were pool balls on a pool table? We've seen plenty of examples of what happens to asteroids after the result of a collision. So, there was the OSIRIS-REx mission, went to visit asteroid Bennu, and then there was the Hayabusa 2 mission, went to see asteroid Ryugu. And both of those are rubble piles. They are just a pile of rocks that is sort of loosely accumulated together. And so what happened? Well, two asteroids smashed into each other, or larger asteroids, and then the debris collected together into this sort of collection of rocks, of boulders. And so no, if you have two asteroids that are crashing into each other, they are going to just shatter each other and create just debris, little bits and pieces. And then depending on the direction that debris is moving, if it's moving together, then it will recombine from gravity. And now you just get this ball of rocks. And so that's the result that we see. We've seen enough of these rubble piles that, this is what happens to asteroids when they collide with each other. So you probably started out with, much bigger asteroids, and then they crashed into each other and broke into smaller, and crashed into each other and broke into smaller. And we see families of asteroids that share like very similar chemical characteristics. So they were once part of a larger object that had been broken up multiple times. And the universe is just, or the solar system is just grinding them all down into dust. Sorek 311, will we ever penetrate Uranus's atmosphere? So with the missions that were sent to Jupiter and Saturn, they included an atmospheric probe. The Galileo mission had an atmospheric probe on board. And so when Galileo arrived at Jupiter, it dropped the probe into the atmosphere. The Cassini spacecraft, when it arrived at Saturn, it was the atmospheric probe. It crashed into the atmosphere of Saturn and was able to provide a little bit of data before it burned up. So you would assume that if a mission actually went to Uranus, they would drop a probe into the atmosphere, or Neptune. We still don't know, it would be really useful to know about the upper layers of the cloud decks of those ice giant worlds. Did you know that you can watch the same video with no ads and get a bonus question over on Patreon completely for free? We call that Q&A Plus. And this week's bonus question, would Planet 9 be categorized as a planet? I'll put a link in the show notes. All right, those are all the questions that we had this time. Thank you, everyone who put your questions into the YouTube comments, everybody who joined me for the live show. Now, I'm going to be traveling next week, so we're going to have to reschedule the live show. I'm not sure the exact date, but I will put that somewhere here on the channel, so you'll see when that's going to be. Now, I'm going to chat about my recent media watching and playing, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Balak, Cy Nelson, Dark Finga, Dave Verioff, David Gilton, David Matz, Evan Pro, Greg Feely, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Sitz, Michael Purcell, OneStepForAnimals.org, Paul Rabach, Ren Kaidu, Richard Williams, Sean Sargent, Stephen Fowler Munley, Team 49, Telescopes Canada, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So just to keep you up to date on what we're playing and watching here in the household, first up, I'm a Path of Exile enjoyer, and the original Path of Exile 1 just released its season 3.27, and so I have been playing. And so far, it's been a banger. It's been a very, very good season. And the biggest reason, the one that, they could just, stab needles in your eyes and I would still want to play this season. And that is because they have asynchronous trade, that you can just go on to other people's hideouts and you can just buy their stuff. And then you can sell the stuff that you want to sell. And this is something that they have been resisting forever, and they've finally done it, and it's terrific and totally changed the game. So if you've ever wanted to play Path of Exile and were frustrated on how hard the economy is, it's better than ever now. We just finished watching season 4 of The Witcher, and this is where they've replaced Henry Cavill with Liam Hemsworth, and he's fine. It's good. In the beginning, you're like, oh, it's obviously it's a different actor, and then he has the same kind of gruff response as Henry Cavill, and the fight scenes are good, and it's fine. It's fine. It's perfectly acceptable. We were trying to come up with a good pun for it, maybe The Switcher. Anyway, so watch that. Season 2 of Dan to Dan, which is bonkers, and I think one of my favorite recent anime. Rewatched Cabin in the Woods, which I think, I'm not a horror enjoyer, but we rewatched that movie and I really love Cabin in the Woods. It's in my top 20, maybe top 10. And then a movie that's been on my list for a long time, but I've never really watched. It's called Stalker. And this is a 1978 movie from the Soviet Union and is telling a science fiction story called Roadside Picnic. And it is very weird and very slow, but it is also good. and you sort of spend the next couple of days wondering what it is that you just watched. So if you want a kind of existential movie, check out Stalker. All right, so that's what we've been watching this week, and I'll give you another update in I'm sure a few more weeks on what we're watching next. We'll see you next time.